Hey folks, so in this video we're going to introduce a new graph problem. So we're going to call this the pathing problem, which is really kind of a more specific version of the search problem. Search problem is what we've been talking about. There the concern was, can I tell whether two nodes are connected? Now the pathing problem asks the same question, but it has this additional part. It says that if two things are connected, what is the path that connects them, right? And all of a sudden, this is a very interesting thing to ask, right? Before it was just kind of a Boolean. Can I get from A to B, right? Now we don't just say, yes, I can get from A to B, but we actually know all the different nodes to get from one place to another. So let's take a look at this. Up top, I basically have my public class paths, right? Which is basically my API, right? My API have all the different functionality that I want. Now, the stuff here I have is pretty similar to what I had before, right? So I still have the same constructor, and my constructor is basically, what my constructor is doing is basically taking in the graphs, taking a starting position, right? And it's initializing everything, right? So it's going to go find where all the paths between this one point and something else. And then I have, right, the equivalent of marked is the second one. So has path 2. Basically what that's doing is checking to see is there a path from that starting node that you picked in the constructor and something you've passed in, right? Is there a connection, right? Yes or no? Okay, so that's kind of just like marked. But then the really interesting one is the last one there. So path 2. Path 2 is actually going to be a method that if I call it, it'll return me the sequence of edges that took me from S, right, my starting position, to that V, right, the position that I'm looking for in the graph, right? So what is the sequence of steps, right? So this is really cool. Let's jump down to that diagram on the bottom. So my diagram here, I have kind of the same graph as before, and then I have some of the same questions as well, okay? So initially I'm basically saying, okay, I'm going to do a path starting out of 0, right? That's great. Then I can do the same thing I did with marked, right? In the previous example, I can check to see is 2 connected, is 4 connected, right? One of them is, one of them isn't. But then I have this brand new function, which is path 2. So I can do a path 2 on 4, and path 2 on 4 gives me back 0, 1, 4. So basically what it's telling me is the way you get to 4 is like this. You go from 0 to 1, and then 1 to 4, right? I mean, we have 3 nodes in there, right? But there's only 2 edges between them. And so this is kind of much more interesting, right? So I have this one path, right, that gets me from this location to this other location, okay? So that's what we want to look at, right? We're going to basically have some new algorithms, right? We're going to start with DFS, and we're also going to introduce another one called BFS, or breadth first search. Their whole job is basically to get me the exact path that I'd got from one position to another position. Now, for us, right, this is going to be, well, we're going to make it more valuable. Initially, right, it's going to be a little bit hard to figure out what this path should be, hard as in, like hard to use the result from it, and then we'll get something a little bit better. So first is a thought for you guys, and this is kind of a question of slides, something for you to maybe think about for a second, so we're talking about we want the path between the two nodes. Is it the only path, or is there many, right? So is there one or many paths here, right? From 0 to 4, what do you guys think? Well, in the graph itself, there's going to be a bunch of paths, right? I can go from 0 to 1 to 3 to 4, right? I can go 0, 1, 3, 1, 4, right? I can go 0, 1, 4. I can have all these different paths that go from 0 to 4, okay? So somehow the point here in this initial thing is we just want a path, right? Some path, it could be any path, right, that gets us from 0 to 4, right? That's what we care about right now, and that's what's going to be our current problem. And for us, it's actually going to be enough to update DFS to track how it moves to the graph in order to get an answer to that, right? In order to get the answer, what is a path from 0 to 4? Now, that by itself, though, maybe isn't the only thing I want. A better question to ask, and the one we'll try to get to, right? It'll take us a little time to get there, but what we want to do is find what we call the shortest path, right? So it would be ideal if the path that gave me was like something up on the screen. So I have 0, 1, 4, right? That's a shorter path than me doing, 0, 1, 3, 4, 0, 1, 3, 4, right? That has an extra node and an extra edge in it. I don't want that, right? So that's something that I don't want, right? So I don't want that path. I want this path over here because it's a little bit shorter. And so that's what we're going to try to work towards, right? We're going to work towards finding the shortest path. Now, we're going to start basically with the assumption that all these paths have basically a weight of 1, right? So it costs 1 to traverse an edge. And that's going to be enough for now, right? But in the future, in other modules in this course, we'll actually introduce the idea of there being little weights or little prices on those different edges, and that making more of an impact in our costs. For now, we're just looking for the shortest path from one node to another, given that the length of it is calculated in terms of the number of edges that it takes to get there. So all right, so having said that, in the next video, we'll take a look at how we would update DFS to get a result like the one that I've drawn up on the screen. Okay, so the question here is how can we update DFS to solve this pathing problem? So I have upon here basically the code for DFS, just a few things that are new. Like for example, I have a new array called edge2. So let's take a look at this and basically see all the new parts that have been added. So most of this is the same. For example, marked is the same, S is the same, right? Constructor is kind of the same as well. Let's see, this is the same, right? All of this stuff is the same. Basically, right, the new things, right, so far are an edge2 array and then initializing that array. And we'll get to what it does in a second. A lot of this is kind of the same as well, right? So this is all the same. And then there's a line there where I initialize edge 2, that's going to be new as well. Let's see, this is basically just returning marked, right? That makes sense. And then this thing here at the end is new, okay? So I have kind of this new edge 2 variable I'm adding, and it shows up in a couple different places, and then I have kind of a method at the end that really does involve it. So what's the idea here? The idea here is that I'm going to add an extra array, right? It's going to be side by side with a marked array to track how I got places. So edge 2 basically says, what edge did I take in order to get to you, right? So I'm looking at some node, and if I'm looking at a node, I must have gotten there from somewhere else. So I'm basically going to be writing down what is that node. So where did you come from, right? I'm going to write that down. That's almost the equivalent of like, if I have a little graph like this, and I have, A and B, I want to write down how I got to B, right? I want to know that the way I got to B was via A, right? So I got from here to there, right? And the way I'd represent that is by having the array having an entry that looks like this. Edge 2 of B equal A, right? So how did you get there? I got there via an edge coming from A, right? So that's what we want to have. So we basically initialize our array, right? We declare it, we initialize it with all zeros, right? And then we update it, right? So as we basically make new calls to DFS, right? As we move through the graph, as we go explore further and further, what we do is we update that edge 2 array, and we say, okay, I'm going to go explore W, so I'm going to write down W. I got to you via V, right? So I'm going to basically make a note of those little arrows. And so at the end of the day, I'll have basically my edge 2 array, which has been populated with basically every edge noting down, or every node noting down how you got there, right? What edge or what node did you come from, right, in order to get to every other node. Note that this array should only be filled out ever once, right? So I shouldn't ever change the values inside of edge 2, right? And the reason for that is if you look at the code, well, the only time you do an edge 2 is if it's not marked, right? So basically marking it and doing edge 2 go together at the same time, right? So you only mark it once and then you never touch it again. Well, when you mark it, that's going to be at the same time that you're doing that little labeling of how did I get there. So that little labeling will never change, right? It'll always be the same, right? You only get to explore something for the first time once, right? So that label should always be the same. All right, so that's kind of how it's integrated in the function. Now let's take a look at the bottom in terms of that larger method. So this larger method is called path2. And what this job is basically to find what is the actual nodes that were traversed on the way to this target point. And so what you have here, right, is first of all, you gotta check, did you actually find a path or not, right? If you didn't find a path there, what's my point, right? I just need to return null, there's nothing to do. And then, right, let's say I do have a path, what do I do? Well, I'm going to create a stack. I'm going to create a stack basically just as a data structure to throw stuff into. I could use something else like a queue or a list or whatever. For now, I'm just going to use a stack because it'll be kind of the easiest thing for me to manipulate. So I have a stack, and then what I'll do is I'll have this loop. And this loop looks maybe a little bit different than for loops you're used to seeing because kind of the ending point and starting point are a little bit different. So we have our loop, and our loop is basically saying our variable is, of course, x, right? Our loop is saying start at v, right? So start at the node that you want the path to, right? So v might be this node over here, right? This node over here, like b, right? That's maybe the place I want to start. So start there, right? And then your terminus, right, is basically say you're going to loop, well, x is not equal to s, right? So keep on moving through the graph, exploring edges, while you don't get back to the starting node. And then the way you update it, right, is you basically say every time x equal edge2.x, or x equal edge2 of x, right? So basically what that's saying is the way your for loop is incrementing, right, you're moving through your data, is you're going to move by saying, okay, I'm going to look at what is the edge that got me where I am currently, and then update myself to be the node that edge is coming from, right? So it's like I'm asking, how did you get to me? Now go and explore that person, right? So I'm basically working my way back through the different nodes that led me to where I started. And so I have this loop, and I basically go and visit everything one at a time, and one at a time, I put each of those elements onto that stack, right? Put them all on, and at the very end, I kind of finish it, right? Because I have to put on S. Already you know, right, that my loop starts when I get to S, so I'm going to exit out before I ever get to add it. So my last step there, right, will basically be to just push S onto that stack. And so yeah, that basically gets me my entire path, right, that it took me to get to that node, right, from the starting location. Of course, there, right, there's a note from before, which we kind of already talked about, but this particular path here, right, we have some concern on, is it going to be the shortest path or it's not going to be, right? And actually, maybe that's something for you guys to think about. Is this going to be the shortest path or not, right? In terms of DFS, we'll give you the shortest one. What do you guys think? Well, the answer here is actually going to be, it's going to be no, right? And you could actually go and look back at some of the examples we've done. If you look back at, for example, the visualization we did for DFS, you notice that some of the pathing it does is basically just running really deep into the graph and kind of just getting lost before it backtracks. It's not making an effort to go and see things, in the shortest path possible. It'll actually try to kind of meander around the graph, just going deeper and deeper, rather than working out in a slower pace. Ideally, what we'd have some sort of algorithm which maybe works out systematically. Maybe it starts at the middle, goes to everything that's its neighbors, then neighbors of neighbors, and neighbors of neighbors, right? If you did something like that, well, then you're kind of going to creep out slowly, and probably the paths that you'll find are going to be the shortest paths as you move through it. So that would be ideal, and in fact, that's what we're going to start talking about in the next video, where we're going to introduce the idea of a breadth-first search algorithm.